Good afternoon. This is Miss Dagenford. I hope you're staying warm in this crazy weekend weather. We're going to get a head start on our population genetics, and this is a nice way to combine and see how we can use math and statistics and genetics to all look at how populations can change over generations and years. We're going to be looking at the frequencies of traits. Now, we're going to be doing that by looking at allele frequencies, but then also we're going to end up looking at genotype frequencies as well. Now, we're going to start, let me get you thinking about a set of assumptions. And you want to think about the fact that unless certain criteria are made, if you shuffle the same deck of cards, the frequency of the cards is going to be the same. Now they may, you may have more hearts in one pile than the other pile, but within that entire deck of cards, the frequency of the cards stays the same. And so we had two gentlemen. One was a geneticist and one was a mathematician who kind of combined forces, and so they both get credit for this concept, Hardy-Weinberg equilibrium. But then since then we've found papers of yet another scientist, Castle, who kind of dabbled with this as well. So they have not incorporated his name into it, but it should be the Castle-Hardy-Weinberg equilibrium. So there are 5 assumptions, main ones. There are a couple of other ones that you see as well, but that there should be no mutations in the population. Mating should be random. In other words, every animal has an equal chance at mating. Something related, no natural selection. Every animal has the same likelihood of reproducing, but also surviving, having the same number of kids, the same fitness of all the kids. There's no gene flow. There's no emigration and immigration. And then the population is large. Now, all of these assumptions need to be met in order for a population to stay stable. Otherwise, it's going to change the frequency of the genes, of the traits. Now, conventionally, when we're looking at the population, we look at alleles, and the simplest way is to look at one dominant and one recessive allele for a trait. Now, you can get more complicated than this, but we'll start out with one dominant, P, and one recessive, Q. So, for instance, in our fun little example of Santa's reindeer, if we continue to use our symbols, big B would be black nose, little b red nose. If we were to look through this population, well, here's Rudolph right here, and we know that that means Rudolph has to be little b, little b. Now, we don't know, and in fact, that's going to be something that comes back by looking at these reindeer, whether or not they're heterozygous or homozygous dominant, but we do know they have a black nose, where they certainly don't have a red nose. And so let's just, for the sake of argument, say that this guy is homozygous dominant. We have heterozygous, another homozygous dominant. So if we count up the number of big B's in this little population of 4 reindeer, 1, 2, 3, 4, 5 out of 8, P, that would equal 0.625. That would be our dominant allele frequency. And then 3 out of 8, which would equal 0.375, that would be our Q, our recessive allele frequency. Now, that was for our reindeer. If you want, we can have a little bit of practice. Let's say that we have big B, which means black fur for the pigs or skin, and then little b, which would be like a pink or a ginger color. Now, let's just, let me go ahead and give you some of the black ones. Let's say he is homozygous dominant. Let's say he is, let's say he's heterozygous. And let's say he is heterozygous. Now, you should be able to tell me what the frequency of big B and the frequency of little, this would be P, this would be Q, doing the exact same thing. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 pigs. So you're going to be setting up 2 fractions. Now, you got to be careful here because I just did something incorrect. There are 15 pigs. How many alleles do we have? And that's kind of tricky. You got to remember that. So there are 30 alleles. And so you're looking for the frequency of the alleles. Just like I did with a reindeer, you had 1, 2, 3, 4, 5, 6, 7, 8 alleles. So there are 15 reindeer. We need 30 alleles. So why don't you take a second? You know what the recessive is going to be because that means they have to be little b, little b. So see if you can figure out how many little b alleles are over 30 total, and then let's see what we can do with that. Now, we get into what the mathematicians were able to figure out, and that is how can we use the math that we have available to see how these change. Now, let's go back and do a quick review with probability. You've done this in your math classes. We touched on it with genetics. Probability, when we're looking at probability, we know that the sum of all possible outcomes must equal 1. Now, there's a couple of rules. We talked about the rule of and. We're going to talk about the rule of or. If you have the rule of or, that means we add the probabilities. So a real simple one, what's the probability of heads or tails? Now the probability of having a head is 1/2. What's the probability of getting a tail? That's 1/2. And you would add those together to get 1. Now, the way you want to think about this in your mind is it could be heads or it could be tails. Or it could be tails. Well, that means those are the two outcomes. It's going to be one or the other, and that's going to equal 1. Now, does this work with what we're talking about with alleles? Sure it does. You can either get the dominant or the recessive. So same thing, you can either get the P or the Q, that's going to equal 1. So handy dandy, we can just say we could either get P or Q, and that's going to equal to 1. So these are going to be your allele frequencies. That's what we're going to be studying. Now, just to go back and prove it to you, just by the numbers, 0.625 and 0.375, lo and behold, that equals 1. Those are all the possible outcomes. Now, does this work with our genotypes? Well, yes, it does. But this time we've got to apply the rule of and. So imagine for a second we've got big T, little t, cross big T, little t. Now, you want to imagine for the offspring. The offspring, of course, this parent is going to give allele number 1, and then this parent is going to give allele number 2. Remember, we're thinking like, imagine this is in the Punnett square. We're looking at like the possibilities of the offspring. So remember, for allele number 1, we can, we have P plus Q equals 1. In other words, that parent could give that allele or that allele to get 1. Over here, you can have that allele, 1/2, or that allele, 1/2, and that's going to equal 1 as well. So here's our two equations, P plus Q equals 1. Now, here's what's kind of quirky. So what's the probability of allele number 1 and allele number 2? And so if we want to look at that, so let's just plug in the equations. We've got one equation for allele number 1, that's P plus Q. And now and in probability means to multiply. We've already used this rule. What's the probability of having black nose and cannot fly? Well, we've done that before. So now we're just saying, what's the probability of getting one of the allele number 1s and one of the allele number 2s? And so we'd have P plus Q, and we're going to multiply those. Now this, mathematically, you've done before. This is nothing more than P plus Q squared, and that we can do. and that would be p squared plus 2pq plus q squared equals 1. So these end up being our genotypes because we're looking at the genotype that has one allele, either a big T or a little t, and the other allele, big T or little t. And remember, the idea is we're talking about probabilities. They all must equal 1. So really, we're just saying, all of the possible outcomes of this are going to be equal to 1. Now, well, that's no surprise. Now, what do these mean? P squared is the homozygous dominant, 2pq is heterozygous, and then q squared is homozygous recessive. Now, if we really want to prove our point, let's we can go back and we can look at our frequencies of our reindeer. Well, one of them was our 0.375 squared. Oops, 375 squared. Now, if we square that, we should be able to go back to our lovely gatherings of our pigs. Now, I don't want to give you too much because this needs to kind of be digested a little bit. So we can pause right there, and we'll talk about this chart when we come to class. But we want to do a couple of problem sets in class and really start hammering home what this means. But just to kind of give a quick review, this was our allele frequency, P plus Q equals 1. This is our genotype frequency, P squared plus 2pq plus q squared equals 1. So that's kind of your introduction to the Hardy-Weinberg. Have a lovely day.